Hello, and welcome to Storytime with Ty. Now, let's welcome our host, Ty Tracy.
Thank you once again for joining me as I share another exciting literary classic. This will be an amazing tale full of tension, diverse domains, and ultimately being stretched to the limit. Ladies and gentlemen, this is the tale of Titin. Once upon a time, there was an unusually large protein. He longed to be called the name he had always chosen for himself, Titin, but everyone continued to call him by his horrendous birth name. Proline, glutamine, valine, lysine, valine, glutamine, glutamine, valine, lysine, glutamine, proline, valine, proline, proline, lysine, valine, glutamine,
Whoa. Hold on a minute there. For those of you who don't know, Titin has the longest scientific name in the English language, and we are not waiting around for that. So, let's leave our friend here for a little bit. I'll show you all the cool things about Titin.
As said previously, Titin is the largest protein known to science, having over 30,000 amino acids on average. Wow, that's going to be quite a mouthful to say all at once. Coded by gene Titin on chromosome number 2, Titin is found inside the sarcomeres of striated muscles. In fact, Titin is the third most abundant protein in your muscles. So, why do you care? Well, Titin does a lot. It acts as a molecular spring in the sarcomere to counteract tension. It keeps the thick filament centered during contraction. Titin is a structural framework associating with other proteins in the sarcomere. And finally, this heavyweight participates in molecular signaling. All of these are incredibly important functions, but for the sake of time, we will just focus on the spring aspect. How's that sound, Ty?
Alanine, valine, lysine, glutamine, glycine, cysteine, tryptophan, proline, glycine, valine.
Okay, I guess we'll just go on then. So let's look at the physical aspects that make this protein such an ideal molecular spring. So, Titin is 1 micrometer long, spanning 1/2 the sarcomere. Its N-terminus is bound to the Z-disc at the Z-line over on the left, and the C-terminus is at the M-line halfway through the sarcomere. Throughout this protein, there are many phosphorylation sites and even a kinase domain at the C-terminus. These are used in the other functions of Titin mentioned earlier, but we will choose to focus on the structural aspects of the A and I bands and how they help act as a spring. First is the A band. This sequence is highly conserved since it acts to attach to the highly conserved myosin thick filament. It will bind to both the myosin and the C protein. Throughout the A band, you will find long-range repeating amino acid sequences known as super-repeat. If you compare the structure of myosin and the A band, you will see these repeats match the myosin thick filament repeats. Cool, huh? This band is made up specifically of 2 main globular domains, immunoglobulin C2 and fibronectins 3. The immunoglobulin-like domains, as you can see, are composed of 2 sandwiched beta sheets. Each sheet has 4 antiparallel beta strands. Second, the fibronectin domains are very similar. They are also made up of antiparallel beta sheets, but this time they have about 4 and 3 for each domain. However, the A band is not elastic. Now you're probably wondering, how is this molecule a spring if it's not elastic? Well, that's where the I band comes into play. Ty, would you like to explain this?
Glutamine, alanine, glycine, cysteine, tryptophan. Glutamine, proline, cysteine, alanine, glycine.
And I guess never mind. Anyway, as I said, the I band is elastic, able to act as a molecular spring to counteract passive and active forces on the muscle. To do this, the I band is made up of 2 domains, immunoglobulin-like domains and PEVK segments. First off, we have our old immunoglobulin friends. These domains are extended under low stretch conditions. So these would be conditions similar to passive or low muscle tension. So these domains are normally folded into a 7-strand beta barrel structure. Now when they do unfold, the outer domains will unfold first, followed later by the more central domains, as you can see in this figure. Snuggled in between the immunoglobulin domains are many PEVK segments. These are the segments that extend under high stretch conditions. Also, they have no recognized secondary or tertiary structures. But they are known for being rich in proline, glutamine, valine, and lysine, also known as PEVK. Get it? It's its name. To sum up the spring-like work of the I-band, first your immunoglobulin domains will extend, with the PEVK regions untouched. But when more force is exerted, your PEVK regions will unravel. This will continue until your titin has stretched as far as it can. Now, this stretching process is reversible. As you can imagine, that is essential for resetting your muscles when you aren't experiencing tension anymore. Current theories for such reversibility include the formation of reversible disulfide bridges between the amino acids. Additionally, by elongating the protein, you are reducing titin's entropy. Now, such reduction requires a force. However, when this force is removed, the proteins will tend towards its more entropic state. This makes such reversibility energetically favorable.
So great! Now you've seen quite a bit about the amazing role titin plays in your body. And who says science isn't fun? Anyway, I think it's about time we get back to Ty and see where we left off in our story.
Glutamine, valine, lysine, and finally, proline. He didn't like his name at all. Exciting, I know. So, let's move on to chapter 2 and hear about how titin could act as a molecular spring when tension started to grow.
Dude, we've already gone over this. It was a blast. But don't worry, I saved you some popcorn.
Thank you for watching Story Time with Ty. Tune in next week to hear Ty say,
I quit.